Assalamu alaikum dear students, I'm Engineer Abdul Basit and we are in week number 4. This is part 2 of this week. Okay, in total we have this is 7 lecture and this is number 8. Okay, the topic we are going to cover is Reynolds numbers. Okay, uh, in previous tutorial of this week number 4 we have discussed different types of fluids and we have also discussed Reynolds number and laminar flow and turbulent flow. Okay, so this is a number that can differentiate us the laminar flow and turbulent flow. Okay, practically experimentally how we can determine the Reynolds number. So before going there, let me discuss some main aspects of the Reynolds number, how we are determining this and why we need to determine this, and actually what is the mathematical form of the Reynolds number. So let me move on. This is that expected results, okay, that we may get from this experiment. That for example, if we are having a fluid in this container and that is flowing through this pipe, okay, so the magnified form of this the picture of this form or this pipe will be like this. Okay, the magnified picture of this pipe will be like this. Okay, so for example, we are having a dye, red color of the same viscosity as that of the water. Whenever this water is flowing through this pipe, okay, if the water is giving us this straight line or the dye is moving in this straight line, so it refers to that it is a laminar flow. Okay, and if the dye is giving us this zigzag form of flow, okay, so this type of thread, and then it will be called referred as the transition zone. And whenever the dye is completely merged or dispersed through the water and you cannot differentiate whether it is water or dye, it will be a complete solution of these two things. Okay, so you can say then this is a turbulent type of flow. Okay, from your book that I have uploaded on the portal, you can see that we have three types of flow. This is that picture that is given in at the end of the experiment. You can see the dye is having a straight line. So if the dye is having that straight line, you can say this will be the laminar flow. So this A is showing us laminar flow. Okay, this B is showing us the transition zone. Okay, where you can see some threads of the dye here that are in contact with each other, not completely dispersed through the pipe. Okay, so such type of zone is called transition zone, where you cannot differentiate it whether it is or you can say this is not completely a laminar flow and not completely a turbulent flow. This is something in between. Okay, so then you can say this is the zone where the dye will be completely dispersed in the water flowing through this pipe. Okay, and that will be in that case you can say that the flow will be a turbulent flow. Okay, so this is how you can determine the Reynolds number from the experiment. So actually I wanted to mention something about Reynolds number over here as well. That Reynolds number is actually inertial force divided by viscous force. So this is that mathematical form. Okay, we will discuss that as well. Okay, uh, something different is like, for example, this paragraph is very important that I would like to mention at the start of the tutorial. That is, Reynolds number is, for example, the Reynolds number is between 2000 to 2800. So you can say this will be laminar flow, not turbulent flow. This will be a laminar flow when the Reynolds number is greater than 2000 and less than 2800. Okay, but if the Reynolds number exceeds 2800, the flow is turbulent. The flow will be turbulent. Or you can say I would like to mention this zone as transition zone between 2000 to 2800. This is some correction, and then less than 2000 is considered as laminar flow. Okay, and if the Reynolds number is greater than 2800, so then it is called can be this type of flow can be considered as turbulent flow. Okay, so let me tell you that we have these two types of zones in which, for example, first is 2k. Okay, so whenever the Reynold number is less than 2k, okay, Reynold number is less than 2k, so this will be laminar flow. So L is for laminar flow. Okay, whenever the Reynold number Rn is in between 2800, or you can say less than 2800, okay, and it is greater than 2k or 2000, so you can say this will be transition flow. Okay, so this is the transition zone between the laminar and turbulent flow. Okay, so this is for transition TR. Okay, then if the Reynold number is greater than that of 2800, okay, sorry for this bad writing, 2800, so then this type of flow can be considered as turbulent flow. Okay, so this will be the turbulent flow. Okay, so this is something written over here in this paragraph. Okay, you can experimentally find out how can be this Reynold number. Okay, the simple arrangement for this experiment will be uh, there is a container. Okay, this is that container in which you have water. Okay, and this container is placed for a long time so that the water is completely in rest. Okay, the container is placed for a long time to bring that water to rest completely to the rest. Okay, and then a dye is placed over the container. Okay, and that dye may be of a red color, which can be clearly visible in the pipe or flowing in the water. So that should clear, this color should be clearly differentiating from water as well. So you can say blue color cannot be used over here, either red or green. So that color which is completely different from that of the color of water. Okay, or color of pipe. Okay, so a dye is placed over here. Okay, and this dye is having the same viscosity as that of water. Okay, when this water is completely at rest, okay, thus this water will be somehow filling this pipe as well. Okay, that is connected to this container. This wall will be opened slowly. Okay, and this dye will be opened as well. So you can say this dye will flow through this water that is flowing out through this pipe. Okay, when the flow through this pipe is turbulent, so it means that the all the particles in this pipe will follow its own path, or will be flowing in a straight line. Okay, so simultaneously the dye that is present in this container will also flow in a straight line through this pipe. Okay, so if a straight line is achieved, so then you can say that this is laminar flow. So here are the result. This is laminar flow, this is transition flow, and this is that turbulent flow. Okay, so this is the simple arrangement for that experiment. Okay, here are some specifications given as well. That container is fill that glass tube is 1.5 meter long and 50 millimeter diameter. Okay, the water through the glass tube can be gradually adjusted by regulating the walls. Okay, so there are some specifications given. Then these are the results. So this is that colored form, and this is that picture that is given in your book. Here it is. Reynold number mathematically is actually the ratio of the inertial force to the viscous force. So what does it mean by inertial force? Simple, you can say that density multiplied by v square, that velocity square. Okay, so this is that inertial force, and this is already determined that viscous force will be equal to mu v divided by d. Okay, so this is velocity, this is diameter, and this is that absolute viscosity. So this velocity, this v will be cancelled with this square, so you will get this rho v and d will be taken to the denominators, so then this will be rho vd divided by mu, and this mu divided by rho, so the reciprocal of this rho divided by mu is actually the kinematic viscosity. Okay, so then you can say that this kinematic viscosity can be placed at the denominators, so kinematic viscosity into diameter divided by velocity. Okay, sorry, this kinematic viscosity is here and this is velocity. Okay, so then you can say the Reynold number Rn will be actually equal to this mean velocity of the liquid, diameter of the pipe, and this kinematic viscosity of the liquid. So all these things can be taken from that Reynold number determination experiment as well. Okay, so whenever you are having all these values, you just simply put it over here and then you will get that Reynold number value for you. If that value is less than 2000, so then it will be a laminar flow. If it is between 2000 and 2800, then it will be considered as transition zone, and if it is greater than 2800, so then it will be considered as turbulent flow. So here it is that graphical representation of the same thing that I am saying here. Here it is on this abscissa, or on the x-axis we are having Reynold numbers. This is 10 raised to power 2, so you can say this is 100, 0, and this is 100, this is 1000, this point, and this is 10,000, and so on. Okay, and this is that friction factor, okay, F, and it is having some values over here. Okay, so as much the friction is increasing and the Reynold number is increasing, so simultaneously we are getting a graph. Okay, the friction number at initially it is increased, it is 0.1, okay, and the friction number is now decreasing with the Reynold number as well. Okay, so this zone that is from here to here, this is actually that laminar zone. Okay, so whatever flow that is satisfying this graph is actually called laminar flow. Okay, and the flow which is showing which is in this zone, or you can say from here to here, this is actually their transition zone. Okay, and then after the transition zone, this graph is actually showing us, or you can say the zone from here to here. Okay, that is actually the turbulent zone. Okay, so this is their simple representation. This is something I have taken from internet, and the credit goes to that Google. Okay, so here it is that Reynold number, okay, that can be determined by this formula. Already we have discussed it in previous slides, and this is that friction factor. Okay, you can determine it by this formula. This is that head, this is that length, this is diameter, this is velocity, this is gravitational acceleration. So this is the sample formula which you can use for friction factor. Okay, so here you can say these friction factor are given over here. Reynold number is given on the x-axis or abscissa. Okay, so this is the zone from here to here. This is actually the laminar zone, and this is that critical zone or transition zone from here to here, and from here to onward this is the turbulent zone. Okay, and at the same time you are getting the relative roughness coefficient, that is E divided by D. So this is something different and it's not related to your topic, so I'll discuss it later. Okay, so this is the thing I've already discussed multiple times, no need to discuss it again. Let me solve a simple numerical on the Reynold number determination. Okay, as the formula we have discussed in the previous slides, an oil having kinematic viscosity of 21.4 stocks. Okay, so that it should be converted to meters square per second as well. Okay, and is flowing through a pipe of diameter 300 millimeter. So this is the diameter of the pipe, which should be converted to meters if it is in millimeters. Determine the type of flow. So for type of flow you need to determine the Reynold number. Okay, and if the discharge through the pipe is 15 liters per second. Okay, so this is their discharge whenever you divide it by 1000. Okay, so this unit liter per second will be converted to meter cube per second, as in 1 meter cube we are having 1000 liters. Okay, so this is the form. And stocks, this is 21.4 stocks. So to convert this stock unit to the meter per second, so we have to multiply it with the 10 raised to power minus 4, or you can say divide it by 10,000, divided by 10,000. So this terminology and these things are actually discussed in previous slides. Okay, if you are having any query, so you can go through that slides as well, these tutorials. uh, for solution, we should determine the A first. Okay, because from we need to have the velocity, not discharge. Okay, so that velocity can be determined from discharge by using that continuity equation, that discharge divided by area is actually velocity, or in other words you can say that discharge is equal to velocity into area. Okay, so if you want to find out this velocity, so divide it by area. So area of the circular pipe will be determined by pi d square divided by 4. This is the formula. Okay, and d is given over here, that this is 300 millimeter or 3 meters. Okay, and put it over here, so this will be that area for you. Now discharge is 0.015 millimeter meter cube per second. Put it over here, put the area over here, and then you will get this thing, that is the velocity. Okay, so once the velocity is determined, kinematic velocity is given, diameter is given, so all the things are given. You need to just use this Reynold number equation, where this is the velocity, this is the kinematic viscosity, and this is the diameter. Okay, so put it over here in this equation. This will be the answer you want to have. Okay, this is that Reynold number. So as this Reynold number is less than 2000, okay, Reynold number is less than 2000, so the type of flow is laminar flow. Okay, let me move on to the second example. An oil of specific gravity, that is 0.95, is flowing through a pipeline of 200 millimeter diameter at a rate of 50 liters per second. So this rate actually refers to discharge, capital Q. Okay, and this is the diameter. Okay, and 0.75 is the specific gravity. So from here you can find out that density as well. Okay, so all the things are given. Find a type of flow. So for type of flow you need to find out Reynold number. Okay, Rn. And if the viscosity of the oil is 1 point, so viscosity is also given. So here one thing must need to be mentioned over here, that instead of using this formula, that simpler formula where velocity, diameter, and kinematic viscosity is required, so this was used in the first example. For this example, instead of using this formula, you should use this formula, because you are given with the specific gravity. So from specific gravity you will determine the density. Okay, velocity from the discharge and diameter is given, and this is that dynamic viscosity for you, which is given in points. Okay, so here it is. First of all, specific gravity is given 0.85. This is 0.95, not 0.85. Okay, a bit of correction. This is 0.95. So from specific gravity you can determine the density of the oil. So density will be equal to 0.95 multiplied by 1000. Okay, multiplying it with the unit weight of density of water. So this will be the density of that oil which is flowing in the pipe. Okay, so if the diameter is given, so you can determine the area as well, and once the area is determined, okay, you can determine the velocity as well by using that continuity equation, discharge divided by area. Okay, so this will be that velocity of the oil. Okay, so once velocity is determined, you can find out that kinematic viscosity as well. Okay, so how you can determine that kinematic viscosity? That V is actually equal to I'm sorry for this interruption. This kinematic viscosity is equal to dynamic viscosity divided by density. So dynamic viscosity is actually this absolute viscosity is actually 0.1. Okay, and density is already determined over here. Okay, so this is that equation that we have discussed in the previous lecture. Okay, and then Rn, that is Reynold number. So already I have mentioned that you can use that formula as well, and this one as well. So once you have determined that kinematic viscosity, so you don't need to find use that previous formula. Okay, you can use that simplest formula as well. Okay, so if you are skipping this step, okay, if you are skipping this step, so then you have to use this formula, this one. Okay, this one. Okay, so here it is, putting the values. This is that velocity, this is kinematic viscosity, all the things are given, put it over here. So this is now 3029. So this is Reynold number. So as this is greater than 2800, okay, it is more than 2800, so then the type of flow is turbulent flow. So this is what we can get from the two examples, that whenever the Reynold number from the equation given is greater than 2800, this will be a turbulent flow. If it is less than 2000, okay, so then it will be a laminar flow. Okay, so this is that's all about this lecture. In the coming week, inshallah, we will discuss about the types of pressures, definition of pressure, and different instruments or devices that can be used to determine pressure. One of them is manometer. Okay, so pressure, types of pressure, piezometer and manometer, all these stuff will be discussed in the coming week, inshallah. And I hope you have got something new to learn from this lecture. Thank you very much for watching. Assalamu alaikum.